My name is Rich Ottinger, and I am the Marketing Programs Manager for Park Systems, coming to you live from the Park Nanoscience Center on the campus of SUNY Polytechnic Institute in Albany, New York. Welcome to the 8th installment of Park Systems 2019 Material Science Research and AFM webinar series. Today's presentation is on the topic of QCM and ultra-thin films tandem with AFM. Unfortunately, this month, our featured speaker, Dr. Rigoberto Advincula, had a scheduling conflict come up, so we had to pre-record today's presentation. The presentation does take up just about the entire hour, and in his absence, we will not have a Q&A at the end. That being said, you may still type in any questions you have at any time during the webinar using the questions pane. Dr. Advincula will respond in a follow-up email to the entire group with any questions that come up. It is now my pleasure to introduce to you via video recorded live earlier, Dr. Rigoberto Advincula. Dr. Advincula is a professor of macromolecular science and engineering at Case Western Reserve University and the editor-in-chief of MRS Communications. He is a fellow of the American Chemical Society and is the author of more than 250 peer-reviewed publications. Please enjoy the presentation.
Well, good morning, good afternoon, and good evening to all of you. Thank you again, Richard, for hosting our webinar today. I'd like to dive into the topic of quartz crystal microbalance, or QCM, and its application for investigating thin films, along with the use of AFM, both ex-situ and in-situ techniques. I'm with Case Western Reserve University in Cleveland, Ohio, and we are in the cultural part of Northeast Ohio, where we are at home with the Cleveland Museum of Art and Cleveland Orchestra. I'm a faculty at the Macromolecular Science and Engineering Department, and we do a lot of work related to thin films, surface-sensitive analytical techniques, and 3D printing. Focusing now on chemistry of the surface, interfacial chemistry, nanostructuring, investigative tools for probing phenomena at surfaces and interfaces are some of the things that we have been interested through the years, and looking at its application in nanotechnology, oil and gas, coatings are some of the practical applications of what we do. In fact, I'm also the director of PetroCase, in which we look at the use of polymers as a materials for the oil and gas industry. And part of it is using different types of analytical methods for investigating, again, surface phenomena. So let us go directly now to what we term quartz crystal microbalance, or QCM. QCM is a technique, a method, a instrumentation that makes use of the quartz crystal to investigate many things based on the phenomena of frequency relationship with the deposition of a mass or dielectric. So that the QCM as an electrode or a transducer element typically can be attached together with an evaporated gold on the surface or pattern, enables one to measure the frequency shift as a function of time, or frequency change as a function of loading of mass, or investigation of the viscoelastic nature of films. Such that a QCM experiment using the Sauer-Bray equation can give us the mass of the dielectric material deposited on top of the crystal with a determination of the volume. One can, of course, determine the thickness indirectly based on the density of the material, utilizing impedance analysis together with the plot of the resistance and the frequency allows us to look at viscoelasticity, investigating the adsorption of different types of surface wetting agents and changes in the surface roughness. It's also possible to use QCM as a technique. And then time dependence measurements, or what we call kinetics measurements, which allow us to look at the change in binding or binding assay experiments as mass is deposited on the surface. Again, this can be a type of experiment that can be done with the QCM, either in gas phase, liquid phase, and of course, vacuum. So what we intend to do is, for example, introduce QCM enough to gain an appreciation of the technique, what the underlying principles behind it, and utilize AFM, atomic force microscopy, as a complementary instrument, or look at some of the developed QCM and AFM simultaneous or in situ measurements that have been reported. So applications, I want to specify that the QCM as a technique can measure film thickness. That is, it can rival the use of ellipsometry and other dielectric methods for determining thickness. It's actually very useful in electrochemistry because it can be used to monitor interfacial chemistry or deposition with, let's say, gold utilized as an electrode surface or working electrode. In biotechnology, again, labeling and looking at specific and non-specific absorption of molecules towards enzymes, or looking at very strong interaction, let's say, between biotin and streptavidin, or looking at vesicle formation. Those are some of the things that QCM has been utilized in biotechnology. In the area of functionalization, whether it be disorption or adsorption, that means QCM can be looked at the creation of lipid bilayers, polymer coatings, reactions to surfaces, and other types of sensing applications on a functionalized surface. There are actually limitations in terms of the thickness and sensitivity of this measurement, which we'll try to cover somewhat, in that these are actually in the regime of nanometer sensitivity and nanogram sensitivity. Thus, QCM actually is sometimes labeled as a nano sensitive tool for investigating this chemistry. Other types of thin film formation, whether it's in vacuum, which is a standard technique based on thickness of deposition of gold, evaporated metals, looking at surfactant research, for example, interfacial or surface phenomena, where one is looking at the coverage of a surface, an average surface area of a molecule, the effective absorption of a surfactant, formation of a layer related to the critical molecular concentration. Drug research could refer to investigation of drug kinetics, pharmacokinetics, liquid plating, etching, etching processes that occur with the media, bulk media, let's say for a deposition of metals or removal of material, and in situ monitoring of lubrication or petroleum properties on surfaces, including anti-scaling, anti-corrosion phenomena. So the list can go on, and suffice it to say, QCM is a very widely useful tool, along with techniques like surface acoustic wave or SAW methods and other types of transduced techniques that are very sensitive to surfaces. So just a historical overview, QCM traces its origin to the piezoelectric effect, where the relationship of a vibrating crystal can be related to resonant frequency. Now, along with the ability to prepare what we call AP cut crystals, QCM then is responsible for utilizing this piezoelectric element as a method for sensing or measurement of adsorption based on the piezoelectric properties of this specific cut or type of crystal. In the 1950s, Sauerbrey actually reported in his famous equation the relationship between the frequency decrease of an oscillating crystal and the viscoelastic mass of a deposited material. In that case, it was metal. And the equation actually serves best when utilized in a vacuum condition. However, since then, QCM actually has been used to measure chemistry, chemical events, absorption, desorption, physisorption as well, even in viscoelastic films and media that involves uh, other types of dielectric media or liquids. Uh, in uh, more recent applications, a lot of people refer to QCM as based on the utilization of the dissipation mode of what we call QCM dissipation or QCMD, which is quite sensitive to the viscoelastic behavior of the mass deposited on the quartz crystal surface. So having given the historical background, we can then look at the basis for quartz crystal microbalance. So utilizing a specific 80 cut quartz crystal with several millimeters in thickness, a gold electrode can be deposited on both sides such that one can essentially measure the current or apply a bias or simply do experiments that allow one to measure conductance and impedance. And based on the oscillating circuit, the piezoelectric element is driven by frequency, and this can be related to the mass change. Now, shown below is the Sauerbrey equation, the basis for which is more accurate when it represents a thin and rigid film, shows that the frequency shift or the experimental frequency shift is related to the fundamental frequency of the crystal itself, the area of the crystal, the density of the quartz crystal, the shear modulus of quartz. So all of those are basically constants when referring to a specific substrate, and then the delta M or the mass change. So in other words, the frequency shift can be directly related to the mass change with a specific constant. And that this simplified correlation actually makes the QCM widely useful for mass deposition monitoring, even to the degree of nanogram scale. So along with the advantages of sensitivity, QCM can be used to do what we call in situ or real-time monitoring. Also, as a mass sensing technique, this can be quite sensitive as a transducer mechanism or as a sensor for many types of surface events. And that means that the sensitivity of the piezoelectric media simply has to be corrected with the dielectric media or gas phase to which it or vacuum to which it's exposed to. And as I said, the Sauerbrey equation is quite simple and direct and applies mostly to vacuum, but of course can be extended when monitoring the frequency shift under air, or corrected in the presence of solution or changes in the density viscosity of the media so that it can be represented better. So-called corrections to the Sauerbrey equation include the Kanazawa equation and factors that eliminate the viscoelastic nature of the media itself. Actually, one of the interesting tandem or simultaneous or real-time monitoring could be the combination of electrochemistry and QCM. As you can see, with electrochemistry, one can monitor the deposition or even desorption of redox active material, including metals, including organic molecules, including polymers, which can then be related directly to the mass change as the deposition or desorption occurs. Now, the second to the last point, relatively easy to use, is no simple description. It is indeed relatively easy to use. Like any instrumentation, if you are familiar with the phenomena and if you experiment correctly, then the explanation is quite valid. And lastly, the equipment actually is quite inexpensive, ranging to $1,000 to several $1,000s. And thus, this is one of the more accessible transducer experiments that can even be used for sensing or determination of surface phenomena. So as I said, it refers to the piezoelectric effect, the mechanical stress applied to the surface of various enable one crystal relate the mechanical properties along with the applied stresses. The crystal has to be an eccentric material and a material which has a Curie temperature and in the piezoelectric element, that is the temperature above which the material loses its spontaneous polarity and piezoelectric characteristics is a requirement. Thus, the converse piezoelectric effect essentially is the basis for the QCM. Okay. So here we have a picture of the quartz crystal sandwiched between the gold electrodes. So an oscillation stress is applied on this AT cut geometry crystal, and that at the temperature or the correct experiment with little temperature drift, then this transducer element becomes the basis for a QCM experiment or determination. Now, there are actually two equivalents of the QCM model. That is, you have a mechanical model and an equivalent electrical representation. What this does is it allows us to look at the experiment in a more mechanical approach, viscoelastic nature approach, or looking at the electrical equivalent circuit. So, for example, in the mechanical representation, the force applied is typical of a mass attached to a spring. The spring has a constant or compliance, and it has a piston representation referring to the coefficient of friction of the piston. On an electrical equivalent, you can see here the inertial component related to impedance, compliance of the quartz crystal, represented by capacitance, the R referring to the energy dissipation, as well as the static capacitance of the quartz resonator with the electrodes. So I'm just showing this to you to show the basis for a quartz crystal experiment, which has both mechanical or electrical representation equivalent. Now, shown in this equation is the classic Sauer-Bray equation that I described earlier. However, an equation made famous by Dr. Kanazawa relates to the application of the Sauer-Bray equation with a correction, assuming that you have a viscous liquid interfacing with the crystal. Actually, another form of this equation, Marumatsu's equation, again relates to this correction. So in other words, there have been attempts to modify the Sauer-Bray equation when applied to liquid media. One of the well-known corrections is based on the Butterworth-Van Dyke equivalence circuit, which provides a viscoelastic description of the material deposited on the quartz crystal. This is equivalent to an impedance analysis of the QCM resonator, which again can be done using a network analyzer to have a better description of this viscoelastic nature in various media. However, a very well-known plot based on the Butterworth-Van Dyke equivalence circuit shows that plotting the resistance element versus frequency allows one to prepare model uh, viscoelastic interpretation of the deposited film. In other words, by simply measuring along with the frequency shift the resonance resistance and then plotting them in an XY plot, one can have a distinct differentiation between the viscosity and elastic modulus component of the film. So just to show this elastic versus viscous component on the quartz crystal, the schematic diagram shows the differences between the resonant frequency change and the transverse viscosity wave or resonant resistance in various conditions. So A, for example, represents a solid state, totally elastic film. B shows what happens when it's in contact with the liquid. C with a viscoelastic film. D with a viscoelastic film and a viscosity increasing model. Or shown in E is the film thickness dependence to the vibration amplitude, and so on and so forth. So in all these scenarios, one can see that the viscoelastic component can be distinguished on the quartz crystal along with a deposited film that then shifts this behavior as a function of the dielectric material thickness. So what we have here are basic plots where we take the resonant resistance R, which is again measurable, versus the x-axis, which represents the frequency shift, enabling us to look at these various properties or lossiness of the film once deposited in the quartz crystal. So again, A, where you have a zero slope, represents an elastic film property. B shows the viscosity changing upon contact with water. C, when you have this shift in the slope representing a viscoelastic film deposition, and D representing a viscosity change and elasticity change on the viscoelastic film itself. So again, the mass effect can be represented essentially by the factors involving that of the frequency shift and the resistance. The resonant frequency change, by the way, is independent on the contact material type, or in other words, this can be applied to almost any types of films from organic to metal. And what one simply monitors is the change in slope and any correction one does with the liquid media, and therefore applying the Kanazawa equation as well. So just to give you a experimental sample here, this is actually one of the films that we measured in our lab, where you have a plot with a negative slope as shown here. The viscoelastic material means that the property is differentiated from a totally elastic behavior, which is represented by a zero slope. And on the other part, you have a pure liquid viscosity density response, such that this film is more lossy compared to a solid state elastic film, and thus can easily be used to characterize the lossiness of the deposited organic or polymeric material with this plot. Another representation that we have done, for example, is simply monitoring the kinetic or time-dependent studies. So a simple setup here where we have a quartz crystal that we dip on a solution of various concentrations of polymer shows us that over time, the frequency decreases, meaning the frequency decrease and even the modeling of the curve can represent a kinetic or rate model that can be interpreted on the basis of adsorption, or whether it's physics absorption, chemisorption, or different rate models in terms of induction or fast deposition kinetics versus equilibrium. I will not be able to describe a lot of those type of experiments, but suffice it to say, other than looking at the frequency shift, viscoelastic nature, as I described, QCM is one of the best methods to investigate time dependence phenomena or kinetics on surfaces or absorption. Now, let me focus at this point on QCMD, which is one of the more favorite and if not widely popular variations of QCM. In QCMD, or dissipation monitoring, this is essentially an extension of the QCM method in that once an oscillating circuit is driven on the Pierce crystal, one can short circuit or essentially stop that application of the oscillating circuit and then simply monitor the dissipation of energy. And by observing the character of that dissipation, one can actually monitor changes on the dielectric thickness, viscoelastic behavior, and even more sensitively, QCMD can be used to characterize the viscoelastic nature of the film deposition or deposited film. In fact, QCMD is quite popular and relative in the biosciences in that it has somewhat changed or rivals what has been done with surface plasmon resonance, a very popular method for determining assays or binding assays in biomolecules or enzymatic action. So in QCMD, as you can see here, a quartz crystal is driven at its resonance frequency. The drive circuit is short-circuited, and then the exponential decay of the oscillation amplitude is monitored. Thus, the dissipation is obtained from the single exponential decay constant, which describes the decaying nature of the oscillating amplitude. So with different media or viscoelastic material, this character changes. And the dissipation can be related to the resistance and the inductance, which remains constant unless there is an acoustic resonance in the film crystal, and the angular frequency at series resonance. In fact, with impedance analysis or the use of a network analyzer, this can be observed with several harmonics, and the sensitivity of each harmonic can be more accurately represented with specific experiments. And more on that later when we look at some specific publications. Nevertheless, as you can see here, Experimentally, what happens is in a normal QCM experiment where you have a driving circuit, uh, the amplitude as shown here is constant, and then depending on the frequency, that's A. However, in B and C, the power is simply shut off to the sensor, and the oscillatory energy decay is monitored. So to differentiate the property of dissipation with the rigid mass, uh, uh, usually you have lower dissipation values on a rigid mass or elastic property on a film. On the other hand, if you have a very lossy film, uh, viscous film, or simply a soft matter, which we sometimes refer to most polymers and biomolecules, you will have higher dissipation values. So that particular difference can be sensitively measured in a QCMD experiment. Now, another way to represent it is by uh, monitoring the dissipation over time, or if you look at the frequency, which represents as a decrease in frequency with mass loading, the dissipation properties varies. So if you have a rigid film that is deposited on a surface, the dissipation is not easily observed, especially in a dry condition or in a vacuum or air media. On the other hand, if you have molecules that are deposited on a viscoelastic media or liquid media, simply put it, this dissipation will be observed and measured uh, as well, and that represents the change in or monitoring with the shadow of the circuit. On the other hand, if the layer itself is viscoelastic under liquid media, then you will also have a shift in the dissipation. In other words, QCMD is sensitive both to the viscoelastic liquid media and the viscoelastic nature of the deposited film itself. Okay. So here, for example, is a commercially available QCM non-dissipation mode, meaning one can measure the frequency and even the resistance. So you can perform a typical experiment under vacuum or even liquid with correction. But as an instrument, the non-dissipation mode QCM is widely available and has been used in many, many experiments as well. And there are several companies out there that have commercially available QCM systems. However, a QCMD is a more expensive variation because of the flow cell and the experimental configuration, as well as the data analysis package that has been put to it, or simply a black box approach, which is quite popular with people who don't want to dwell with the configuration, but totally adjustable in parameters. So this one is from Violin Scientific that has been utilized in a number of labs and actually developed partly in Stanford and also with Kanazawa. Has been around for a while. So QCMD dissipation uh, are available instruments as well. So having introduced all I can with QCM, QCMD, I'd like to give a short description of the atomic force microscopy experiment. And then I will close this webinar with combinations of the two experiments, QCM, QCMD, AFM, and then finally instrumental configuration where the two have actually been simultaneously utilized. So in AFM, atomic force microscopy, which is a surface probe microscopy method, can be used to analyze surface forces, viscoelastic forces, and more importantly, morphology, topology on surfaces as visualized in a micrograph. In other words, other than its interesting probe for surface properties, um, surface forces, viscoelastic forces, conductance, electromagnetic behavior, etc. Overall, atomic force microscopy is still a microscopy or indirect microscopy technique that you can visualize the topology or morphology. And again, just to show you the relevance of this AFM technique, it's based on the movement actually of a piezo element itself, either based on the sample probe or the laser diode probe, and it relies on a probe tip. Probe tip can be made to be very sharp, or it can be made to be very sensitive, but the position or deflection of the tip or simply movement of the raster tip can be sensitively uh, um, detected in a position sensitive photodetector and thus recreated to form an image, which we can then observe as an AFM micrograph. Now, let me emphasize here one of the important differentiation of AFM methods is the way the XYZ piezo element is designed. And in most cases, uh, a lot of the techniques out there have various advantages in terms of sensitivity or ability to image, various features, in that many types of techniques have claimed to be non-contact and of course contact mode all the way to STM modes. Uh, the advantages of an AFM can also be related to ability to couple it with other instruments or other experiments. So for example, in the past, we have actually coupled AFM together with surface plasmon resonance and even electrochemistry to come up with an AFM SPR combination. An open system such as the other side of the substrate or surface can be accessed optically or using a QCM circuit enables us to do what we call hyphenated techniques. Okay, so one of the advantages of a system like the Park AFM system is that one can decouple the XY scanner with the Z scanner. This type of decoupling means you have a faster response, no bowing effect. As a true contact mode, you have longer tip usage or prevent its damage. And then, of course, ability to design experiments resulting in high resolution images. So in particular, we have used Park and Extend in many occasions. So one thing that you can modify a experiment is that you can modify the tip itself to have sensitivity on the surface, either by modifying, let's say, a gold tip with various alkane thiols or silicon nitride tip with organosilanes or attaching colloidal particles or even nanotubes. One can improve that sensitivity on the cantilever tip side. On the other hand, the substrate can be very flat like mica or gold 111 or silicon, dope and undoped silicon. One can create various surfaces or substrates that again have sensitivity that can be coupled with the cantilever tip. So along with, let's say, uh, pattern surface or a microfluidic device or controlled flow chemistry, one then has many applications from chemical analysis to physisorption phenomena to biochemical analysis. Again, a lot of these experiments, I do not have time to describe them except to introduce briefly that the versatility of the AFM can be used in conjunction with the QCM to form a broader picture of an experiment or analysis. So for example, with chemical analysis, the sensitivity of the surface interaction can be approached based on force curve measurements. One can also look at the compositional mapping aside from the topology or the phase and amplitude image. So one can do force mapping, friction mapping, electric force mapping, electrostatic or current sensing mapping, and so on. In biochemical analysis, so if you have very strong interaction between the substrate and the cantilever tip, one can look at antigen-antibody interaction, biotin, avidin or streptavidin interaction, DNA, hybridization, and other types of analytical tools dealing with the actual soft matter based on enzymes, proteins, DNA, or other biomolecules. So with that summary, I turn, of course, to the Park NX10, and there's a family of different instruments from Park. We, in particular, use the Park NX10 in a lot of our experiments. So as a true non-contact mode, you can see here that it eliminates some of the possible effects based on repulsive and attractive forces. So in a non-contact mode, we are able to do away with some of these forces and thus a better picture of the total interaction. The result is in a lot of the imaging methods that we have done and others as well, is that we get a very high resolution that contrasts the phase images better, and beyond that of surface features that has deep trenches or patterns, we're able to get high resolution. So again, with this introduction on the Park, it hopefully complements what you've learned about QCM today. So the rest of the time, I will basically look at several publications where they have combined the study of the phenomena or the films or thin films on QCM, AFM, and perhaps other techniques like ellipsometry and even electrochemistry. So the group of Richter actually has many reports where they have introduced the investigation of biomolecules in terms of their adsorption phenomena on surfaces both by QCMD and AFM. So as this example shows, the lipid bilayer or SLB supported lipid bilayer on mica was investigated using QCM and AFM. So with QCM, what is shown here, for example, is the property based on frequency and dissipation shift. Again, the frequency is represented by a decrease in the frequency from 40 to 70 hertz, a difference of 30. And then the dissipation, on the other hand, can be monitored actually kinetically on the solid line. Now, this experiment then can be translated to various conditions, buffered conditions as well, or various concentrations. So the next graph here above the AFM shows another condition which displays a different frequency model shift and a dissipation. It so happens that this actually refers to a lower concentration and hence a lower frequency shift. But the experiment they did was they monitored the AFM image or micrograph in various stages of the deposition. So over time, what they observed is that monitoring the change in frequency and deposition is that the domains tend to form larger and larger domains observed by AFM as the deposition of the supported lipid bilayer takes effect over time. Now, if you go directly to the paper and investigate their conclusions, what they have found is that together with AFM, the formation of larger domains of the lipid bilayer coincided with the equilibrium of or rearrangement of the lipid bilayers once deposited on the surface, but does not show a measurable change either by dissipation or frequency shift. In other words, this viscoelastic nature and actually other data also shows that the viscoelastic nature is somewhat sensitive with the dissipation mode, but definitely AFM gives a correlation on the morphology change at various times of the deposition. So this is what I would call an ex-situ correlation between the AFM and the QCMD result. Now here we have another paper, author Evans and published in Open Access International Journal of Molecular Science, shows the frequency shift was observed for a supported lipid bilayer interaction. I believe this was done both with the mica surface and the modified gold surface in the presence of an ionic liquid, 1-octyl-3-methyl-imidazolene or imidazolidinone. That means that the introduction of the ionic liquid, as shown in the plot, causes a big change in the frequency and the dissipation with various conditions, including a change in pH, sodium chloride concentration. The different colors here actually represents different concentrations of the lipid bilayer. So again, this is one of those ex-situ techniques in that after exposure, the film was then taken and then the AFM micrograph was taken to observe the formation of pits or hills and valleys that remain. Again, comparing the phase image of the supported bilayer before and after exposure. So the conclusion of this study shows that the ionic liquid influences dramatically the equilibration of the film, in that the very strong ionic field actually causes the formation of hills and valleys, which then represents a very dramatic change on the viscoelastic nature, as shown by the extent to which the dissipation changes in correlation with concentration. Here is, again, a third study showing an ex-situ technique. In this case, the paper by Johansson, Ravikian, and Richter tries to make model studies of various proteins and viruses. This happens to be a cowpea mosaic virus, as shown in the micrograph, and then correlating that with the frequency shift and the dissipation properties, along with different sizes of the or models of the virus or molecular weights of the proteins or size of the enzymes. So without giving more details, and as I said, the papers and the references are there for your perusal to deep dive. It shows that the deposition, let's say, of the cowpea mosaic virus, which was verified by AFM, shows a non-agglomerated character, almost a uniform deposition. And both the deposition and the frequency shift actually deviates. So the nanoparticle actually behaves as point bodies or particles. Unlike a viscoelastic continuous film, the particles or copy mosaic virus itself is able to rearrange as point particles on a surface. Thus, even though the frequency shift of the same mass or amount deposited on the surface with various viruses, sizes, uh, the changes in or the equilibrium or rearrangement observed can be correlated with the size of the particle. Now, in this paper, they have several studies too based on model compounds and modeling of that interaction, in that a virus itself or a nanoparticle has a field gradient which have independent points for surface interaction. So unlike a continuous lossy film, the bottom line here is particles absorbing on the surfaces are quite unique in terms of their surface interaction. Now, let me go on to the next three papers to describe what an in situ measurement looks like. In other words, the AFM is simply done together with the QCM experiment. So some reports have appeared actually as early as 2002, but in this paper and some review that was done, uh, one can see, for example, a combined AFM QCM setup. So in a combined AFM QCM setup, you can see here that the cantilever tip is based on a moving XYZ scanner. So it's an open setup. And then you have the dielectric film on a quartz crystal microbalance electrode or transducer. So in other words, you can simultaneously drive the QCM with the oscillating circuit, and then together with a sandwich of the QCM tip and then the sample moving scanner, essentially do both AFM and QCM at the same time. Actually, another variation, so you can do what we call 3-in-1, in that you can do electrochemistry together with QCM and AFM. So the whole experiment is done under liquid conditions where you have electrodeposition, for example, taking place on the sample with a, let's say, cyclic voltammetry or potentiostatic method. And at the same time, you measure the frequency response with QCM. And at the same time, you measure or do the AFM micrograph. So that has been done, that has been reported in a number of papers. So for example, in this paper where they monitor the deposition of zinc metal on a surface, so this custom-built AFM QCM hybrid allows one to do electrochemistry or electrodeposition while simultaneously measuring the frequency shift and the AFM micrograph at various time factors. So in other words, the y-axis could correlate to the frequency shift as well, and the time will be the x-axis, and one can plot, let's say, the continuous deposition of mass because of Sauer-Brace equation. So these graphs are presented by the mass, the frequency shift, or the change even in the impedance plot can be monitored as well or simultaneously for all these experiments. So for example, in B, you have a tapping mode AFM recorded in a concentration 0.3 molar zinc chloride on a gold-coated quartz crystal at various times of deposition. So 0 second, 120 second, 240 second, 360 seconds. So you can see the evolution of morphology by AFM. Now, simultaneously, one is looking at the impedance plot before and after zinc deposition. And here with no baseline correction. But probably more relevant to the AFM image is what is shown below is the deposited mass versus past charge or even as a x-axis of time simultaneously with imaging. In other words, one can actually measure the mass correlating to the different morphologies observed by AFM. Now, in this other paper, coming from the Freight Campitelli papers in Belgium. So here you can see a AFM built together with the QCM experiment, actually a QCM electrochemistry experiment with a liquid cell or flow cell setup. So what you have essentially is an electrochemistry, AFM, and QCM experiment in one. So this micrograph and this graph looks quite complicated, but what it is that you have a common axis, x-axis, which is time. You have the frequency shift. You have the potential shift, which goes to a redox reaction, reduction, oxidation, reduction. And you have a plot of the dissipation, which is also shown. So dissipation, frequency shift, changes in the potential as well, together with the AFM image, all shows a time factor on the x-axis, can all be obtained simultaneously. Okay, so what happens with, let's say, with AFM is that you can have a fixed position on the surface, and then simply as the deposition is taking place, which is shown here, you raster on an XY plot. You simply raster on a point, so going back and forth, back and forth on a fixed area. One can monitor the deposition of the material, which is somewhat observed here in the change in morphology as a function of time. Now, other types of measurements would have been to do a pause on the deposition, scan the AFM, continue the deposition, applied potential, scan the AFM, stop the deposition, and so on. So there are variations of this experiment, which one is able to do the AFM experiment at various time constants. And again, I'll let you refer to this paper and some of these papers to see the variations on this experiment. Now, this paper shows actually from the same group, shows the simultaneous AFM and QCM experiment where we're investigating human plasma fibrinogen adsorption. So what you have here is again a time x-axis, and the frequency observed shift is observed on the y-axis. So since you're depositing the human plasma fibrinogen at a specific concentration temperature, you'll see a decrease in frequency or deposition of the protein over time. A, B, C, and D represents the AFM micrograph at various times of the deposition. So in other words, one can deposit, and this is not an electrochemistry experiment, this is simply a physisorption experiment on a QCM. One can monitor the changes in morphology at various stages of the fibrinogen deposition on the crystal. So I believe these micrographs were actually taken at a post mode of deposition, because in a point deposition where you have a continuous deposition taking place, usually the time constant or time needed for rastering or obtaining an image is slower than the deposition time. So this is again a variation of what can be done in a combined experiment. So I think we ran out of time. As I've said, my objective here was to introduce QCM, to reintroduce AFM, and then to combine the two methods into what hopefully will be useful hyphenated techniques, in-situ techniques for combining both experiments for future reference, and also for designing new experiments in investigating phenomena. So with that, I'd like to thank you, and I'll be happy to answer any questions you may have.
All right, everybody. As I said earlier, we had to pre-record, so Dr. Advincula actually not available live for questions, but you can continue to enter them into the question tab here in GoToWebinar, and we can collect those, and he can follow up with an email. You'll also be able to email them directly to me, and I will have my email up just at the end of this session. So thank you for joining today's webinar. I did get the opportunity to ask my usual final question. So here is Dr. Advincula again with a preview of next month's webinar topic, Surface Plasmon Resonance Spectroscopy, Tandem with AFM.
So yes, Richard, I'll be happy to describe what is in store for next month's webinar. We will be talking about surface plasmon resonance spectroscopy. SPR is a very interesting and important method for looking at surface phenomena, nanostructuring, optical and dielectric properties of thin films. But also in our previous experience, we have actually combined AFM, SPR, and electrochemistry into one. So hopefully our audience will be back for that next month.
All right, so please join us for that session on Wednesday, September 18th, once again at noon Eastern Daylight Time. And thank you all for joining us for this session of the Park Systems 2019 Material Science Research and AFM webinar series. If you have been enjoying the webinar series, we hope you will consider joining us for the 2019 Nanoscientific Symposium on SPM, held November 19th and 20th here at the Park Nanoscience Center at SUNY Polytechnic Institute in Albany, New York. The symposium is a venue for researchers, scientists, and engineers to learn about the latest studies being formed using SPM, featuring speakers including Dr. Advincula and many other industry and academic experts. Visit live.parksystems.com for registration information. Thank you once again for joining. You can find more information about Park Systems AFM at parksystems.com. Please direct any AFM questions you have to inquiry@parksystems.com. If you have any questions specific to this webinar series or questions that you'd like me to pose to Dr. Advincula from this session, feel free to reach out to me directly at richard@parksystems.com. And thanks again, and we'll see you next month.